Well, good evening or good afternoon, everyone. Welcome at the Institute of Theoretical Physics in Paris-Saclay. A number of research fields are studied here in our institute, from statistical and condensed matter physics to cosmology, particle and mathematical physics. And we are interested in understanding how quantum computers and simulators can help to solve problems in some of these research fields. So with the financial help of the European project called Quantum Internet Islands, we took the initiative to organize a series of conferences to try to answer this question. So this is a series of 5 conferences given by renowned researchers having both a clear understanding of ongoing effort and also a long-term vision along these lines. So tonight, it is our pleasure to have Dr. Svore as a speaker. And so she's general manager at quantum software and system engineering at Microsoft, where she leads the Microsoft Quantum Redmond group. Dr. Svore is an expert in quantum algorithms and fault-tolerant software architectures. She has an outstanding vision of future application of quantum computers. So it is really a delight to have you here today, Krista. And thank you very much for accepting our invitation. For the people listening to the presentation, feel free to ask questions in the chat. And I'll read those questions at the end of the presentation so we can have a time of questions. With this, I just give you the room, Krista. And yeah, you can go ahead. Thank you.
Great, merci. Okay, so I'm Krista Svore. It's wonderful to virtually meet all of you, and thank you so much for the invitation to share what we're working on with regard to bringing applications in quantum acceleration to the cloud and to computing more generally. I'm a quantum computer scientist by night, and I lead the quantum software and systems engineering team at Microsoft by day. And this evening, I'll share with you really the area, the types of applications we're looking to bring quantum advantage to, and the considerations we have when we think about quantum advantage and quantum applications. So let's jump in. So I think many of you, read, I'm sure, the global headlines around quantum computing. There's going to be a revolution, as we see here. There's a race to build these quantum computers and bring quantum advantage forward. And, there's even claims that quantum computers are coming, and we should get ready for them to change everything. And I hope by the end of our discussion this evening, you will be able to, be primed with some questions around, what really is that everything? What will quantum computers really, what do we really think they're going to bring advantage to? Which problem spaces should we be looking at? Where should we be, mining for quantum applications and quantum advantage? And how can we get started today to understand those advantages in advance of having full-scale, industrial scale quantum hardware? So first, let's take a definition and understand, what would it mean to have quantum advantage? And here, I want to pull from a definition that Matthias Treuer, who's also on our team at Microsoft, that he presented last year at Q2B, which is a growing quantum conference around both business and technical. And there he presented a definition of quantum advantage, really of quantum practicality, that was really tease up 2 aspects, right? Both speed or improved accuracy, but also time to solution. So quantum practicality yes, we need, for a quantum advantage and for a practical quantum advantage, we need a speed up. We need that quantum algorithm when implemented in hardware to deliver a speed up. And we also need it to be doing that for a practical problem and in a practical amount of time. So when we look at this plot on the right, we have roughly, roughly the problem size that we're looking at versus, say, the time to solution on the y-axis. And classically, ideally what we want is the time to solution, for various problem sizes, to have a crossover point, much like what's plotted here, between the classical solution slash implementation and the quantum solution or implementation, right? So we want that crossover point. We want quantum, the quantum solution, when implemented on real hardware all the way through the stack, to have a time to solution that begins to surpass the classical time to solution at a crossover time that's practical. And I want to define that practical crossover time to be a matter of weeks, right? Not a year, not multiple years. And the reason for that is building this quantum hardware, right? We need to keep that hardware, we need to keep that quantum system coherent, and doing so is challenging, right? In addition, as users, right, or customers of a solution, we don't want to wait around for much more than roughly a month for a solution, right? Practically today, for classical solutions, we will run things for about a month. Sometimes maybe a little longer, but waiting for a year for that solution isn't so practical. And there's also a probability of the hardware no longer maintaining coherence over that time. So let's think about quantum practicality and that quantum advantage, practical quantum advantage, as requiring that the quantum algorithm, the quantum solution as implemented, starts to outperform the classical one at a matter of weeks, right? And it delivers a solution that is either faster or better for a problem that's useful, right? Either useful for science or useful for industry. And so with that definition, we can start to look at the space of quantum applications and ask which ones may outperform today's classical computer solutions. So let's take two comparisons. On the left is a picture of an NVIDIA A100 GPU. And GPUs today have roughly 54 billion transistors, and their cycle time is a little less than a nanosecond. On the right, we have a quantum computer, and let's call it tomorrow's quantum computer. So this quantum computer, it has all-to-all connectivity, which is idealized. It has, say, 10,000 logical qubits, right? We're not yet to one logical qubit in hardware systems today. So this really is a tomorrow quantum computer, right? 10,000 logical qubits. And let's assume that that logical cycle time, so in other words, the operation cycle for a logical qubit that is a well-protected, qubit, a qubit at the algorithm level, is 10 microseconds, right? So you can already see that the quantum computer cycle time is slower than the NVIDIA GPU cycle time. Okay, so let's compare these two machines and running an application on them. So you've probably heard quantum computers will solve big data problems, right? Maybe you've also heard that quantum computers are faster since they explore exponentially many options simultaneously. Well, it turns out both of these statements are not quite true. When we take these two comparisons and we really run the numbers, we find quantum computers, yes, those quantum algorithms have fewer operations in them, but because that reading data, loading data in is slower on a quantum computer, and operation speeds, that cycle time is slower, orders of magnitude slower, in fact. We have to be very cautious as to which applications actually yield that quantum advantage. So if we take these two comparisons again, the NVIDIA GPU and then the tomorrow quantum computer, right? If we look at a logic operation, and so here, when we say logic operation, a logical operation, for example, would be a Toffoli operation, right? So, an operation occurring at the algorithm level. So it's a protected qubit, logical qubit. Or we say we look at a 16-bit floating point operation, where a floating point operation, say, needs is like a 16-bit multiply add. And so we have a few hundred operations underneath that, whereas a logic operation is like a Toffoli operation, or a Boolean operation like an AND, an OR, or an NAND. So let's compare these two types of operations between these two chips. On a GPU, right, you're looking at petaops per second performance for that GPU, but the quantum computer, to do a single logic operation, requires more like mega ops per second, right? So it is orders of magnitude slower. When we compare that for floating point operations, right, which has maybe several hundred operations underneath it within that 16-bit multiply add, we're looking at it requiring around 300 teraops per second on the GPU, and requiring more like 7 kiloops per second for the quantum computer. So it is, much, much slower than your GPU. When we're reading data, if we look at loading data into the quantum computer versus loading data on a GPU, the read rate of the GPU is roughly 10,000 gigabits per second, whereas it's more like 1 gigabit per second for a quantum computer. Right? So you already are starting to get the flavor that we need that many fewer reads, or that many fewer floating point operations or logic operations for that quantum algorithm to outperform the GPU speed. Right? So already I think we can start to deduce that really, when we're looking at something like database search, right, which would be based on the search algorithm, amplitude amplification, Grover's algorithm, right, those are not going to be so, quantum practical on a quantum computer. Quantum computers will instead excel at big compute problems on small amount of data, not big data problems where we require a lot of reading in. So if we take this a step further, this comparison, we can look at, asymptotically, what kind of speedups will help yield the practical quantum advantage we're looking for, right? So it turns out quadratic speedups, when we carry this through, quadratic speedups, the asymptotic quadratic speedups, for example, coming from Grover's search, aren't going to be enough to yield a practical crossover time of a matter of weeks. So when we look at, for example, a single floating point operation, we're looking at, about 4 months is where that crossover time occurs, because of, right, it takes several, couple hundred underlying operations on the quantum machine to do that, and the speeds are orders of magnitude slower. If you have 1,000 floating point operations, the crossover time moves out to 3 centuries, right? And if we were to try to do something like protein folding with the quantum computer, the crossover time is like the age of the universe. Now, 1,000 logical operations, you're looking at 5 months. A hard optimization problem, something like a decade, right? So these are problems where you can start to see that a quadratic speedup is not going to be enough to retain a several-week crossover point. So if we, where can we find practical speedups? Well, we can look beyond quadratic, right? Even though quadratic speedups aren't enough, we also know that there are quantum algorithms for which we have super quadratic speedups. And these super quadratic asymptotic speedups can yield practical crossover times for quantum computers. So let's take an algorithm, right, and look inside the oracle. So we have some oracle, some subroutine that we need to implement in the quantum computer, and of course we're going to make many calls to this oracle during the implementation of the quantum algorithm. And to get a practical crossover time of a matter of, say, 2 weeks, let's look at what can be inside that oracle. How big can that oracle be for such a practical crossover time? So in terms of logic operations, if we have a quadratic speedup for our quantum algorithm over the classical approach, we only have space or time, really, time for 71 logic operations within that oracle. Now, if we have a cubic speedup, so going beyond a quadratic speedup to a cubic speedup, we have time for 13 million logic operations in that oracle. So you can start to see as we move to a cubic speedup or a quartic speedup or beyond, right? Then we can start to get those practical quantum advantages. In terms of floating point operations, if you have a quadratic speedup, we can't even fit one within the oracle, right? We will already, as you saw on the previous slide, will already be well beyond a matter of weeks with a single floating point operation on a quantum machine. But with a cubic speedup, we can fit roughly 21,000 floating point operations within the oracle and still retain a quantum advantage. So, here with a cubic speedup, things are looking a lot better in terms of practical quantum advantage. Um, and and we can fit, millions or thousands of floating point operations in that oracle. So the greater the asymptotic speedup, the better things start to look. And if we look across, there's a whole maze of proposed algorithms. In fact, a zoo of quantum algorithms is maintained by Stephen Jordan at quantumalgorithmzoo.org, who's also on our team at Microsoft. And when you start to sift through all of these proposed applications, right, many of them have a quadratic speedup. And so many of these applications will not be quantum practical, but a handful of very, very important ones will be. And so when we look at these applications, what are the applications where we can get that practical quantum advantage? Well, the simplest one is shown here, right? Where we want to simulate the dynamics of a simple, classically intractable quantum magnet. So here you might have, say, 100 sites that you're looking at. So a lattice of 10 by 10 spins. And at about 100 sites, this problem gets hard classically. So this is really right at that frontier where we can see practical quantum advantage over the classical. And here we're looking at a transverse field Ising model. And we take these 100 sites, we propagate it for a period of time. This requires roughly 100 logical qubits. And when we do these gate operations, we require, roughly, around 30,000 gate operations for this problem. So here, to do these gate operations, we're going to need an error rate on this machine. That required error rate needs to be less than 10 to the minus 6 for roughly this many gate operations and this many logical qubits. But this would give us that simplest practical quantum advantage, right? Something that is hard to do classically that we can improve upon with our quantum machine. Now, the reality here is that the simplest practical quantum advantage problem is still well beyond the capabilities of current noisy quantum hardware, right? The quantum computers we have today cannot yet do this problem, right? We do need those 100 qubits, and we need an error rate that's better than 10 to the minus 6, more like 10 to the minus 7 or better. So that's several orders of magnitude beyond where we are today, but paints a picture of when we can expect to see some practical quantum advantage coming from these machines. Now, more, perhaps even, more exciting, right? While the other problem is this magnet problem is quite interesting from a scientific point of view, from an industrial point of view, the promise of quantum computing really points to the ability to have a computational, predictive computational design for chemistry and materials, right? So really, when we get to millions of qubits, that would be 1,000 to 10,000 logical qubits. We really move forward in the ability to predict the outcome of chemical processes. And even if this is the only set of problems quantum computers enable, to solve, this still could change everything, right? It quite literally could remake our global economy if we're able to improve upon the solutions for this class of problems in chemistry and materials science. So quantum computers being able to help us really turn to predictive design for chemistry and materials, and in particular enabling us to have computational catalysis and photovoltaics, for example. Right. So here with a quantum machine, we can scale to higher accuracy or larger problems in this space as compared to what we can do classically, right, with supercomputers and HPC. So on a quantum computer, we can start to compute the electronic energy of key intermediates and transition states, for example, in catalytic cycles. And let me walk through some of these very important examples here in more detail, because this is such a key unlock, and this really paints the picture of the promise of a scaled, an industrial scale, a leadership scale quantum machine and algorithms. So if we look at clean combustion, right, we can help identify a catalyst to help avoid, for example, toxic gas side reactions that might involve nitrogen oxide. We can also look to improve carbon efficiency. In clean energy, we can work to improve the efficiency of carbon fixation, improve photovoltaics, seek a better material that would help absorb light in a different desired range. And quantum computers here are very well suited to computing those excited states. When we look at clean water, a quantum computer can help us identify a better photoactivated catalyst, for example, than titanium dioxide. Um, and that, for example, helps kill bacteria in water. We could look to a catalyst to help absorb, for example, VOCs on the water surface. In terms of energy efficiency, a quantum computer can help us perform more accurate materials modeling, help us find, for example, a higher temperature superconductor that could help enable lossless power transmission. And just in general, this capability with a quantum machine would enable us to seek better, designer materials for optics, mechanics, electronics, right? And it's really here that the quantum computer is enabling us to understand energies at higher accuracy for larger problems, for excited states, and again, enabling us to move towards predictive design for chemistry and materials. And as I expressed earlier, even if this is the only class of problems we solve with a quantum machine, this still has the ability to really change everything. So if we look at the class of the class of problems to solve with a quantum computer, right, the challenge really is to get there, to get to the types of problems I just mentioned. The challenge really is scale, right? How do we scale up our quantum machine? How do we scale our quantum algorithms and achieve those super quadratic speedups? And it really ripples through the entire system design, the entire stack, the full stack. So here what I've plotted is the number of physical qubits required versus a different set of different sets of applications. And so over the recent years, we've done a lot of analysis of these quantum algorithms and what they will cost when implemented on quantum hardware. And as I mentioned, right, this problem, for example, around understanding, a magnet, as an example, right? That is listed here as a scientific understanding. So for problems that would advance science, we're looking at needing roughly 30,000 physical qubits, translating to roughly 100 logical qubits there, but roughly 30,000 physical qubits required there to advance our scientific understanding. When we're looking at something like cryptanalysis, right, Shore's algorithm as an example, we need more like 2 million or more physical qubits, depending on the key size there. But, somewhere between 2 and 12 million physical qubits to perform cryptanalysis with a quantum machine. And on chemistry simulations, as I mentioned, the types of problems in catalysis, computational catalysis or photovoltaics, you're looking at, 7 million physical qubits required. And in material science, for example, when we're looking at, room, a higher temperature superconductor, for example, in those cases, we will need roughly 50 million physical qubits. Now, these physical qubit numbers are all estimated, assuming you have an error rate on your operations of 10 to the minus 6. And again, there, for a 10 to the minus 6 error rate, that's several orders of magnitude better than hardware today, right? So this is already perhaps you might say an optimistic optimistic view. So the challenge really is to get to that type of error rate for our physical systems, for the hardware, and to get to 1 million physical qubits and beyond to solve the types of problems we want to solve with a quantum machine. So that economic leadership, that leadership class solution really begins closer to 1 million physical qubits and beyond, right? And so there's so we need to look at, what type of architectures are going to enable us to get there, right? What type of device enables us to get there? And then how do we continue to bring down the cost of algorithms and applications so that we can start to meet in the middle, right? Drive improvements and optimizations from both ends of the stack, from the hardware design up and from the algorithm design down. So practical applications, again, require a fault-tolerant quantum machine, right? Logical qubits, logical operations that are protected, and really do require upwards of 100,000 physical qubits, up well beyond 1 million physical qubits. And systems today, as I mentioned, are in this bottom right of this graph. Here we're plotting the error rate versus the number of qubits. And if we look at systems today, we're roughly, you have like 2 to 3 nines in your error rate, and then the numbers of qubits are right around 100, um, somewhere between 50 and 100, depending on which system you're looking at, system design. And we need to get to 100 error-corrected, 100 logical qubits, which is closer to this blue curve here. So we do need to bring this together, right? We need to, again, drive up from the hardware and down from the algorithms to bring these costs down and drive those systems to the upper left of this plot. So to do that, it really does require scaling across the whole stack, and we need a quantum machine that has the right, the right characteristics, right? We need an architecture that has the right characteristics. And what we've learned is that when we look at those, the requirements of workloads of quantum algorithms and applications, it comes down to 3 things: the size of the machine, the speed, and the reliability. So we need the right size. We need quantum devices, right? Qubits that are small enough that you can fit, say, 1 million or more on a single module, right? That you don't have to have long distance communication. And you also need it to be not so small that you can't fit the electronics to control and read out the qubits, right, on that same chip or same module. So you need that sweet spot in size, not too small and not too large. Not too small for the electronics, not too large that you expand beyond a single module where you then require long distance communication, which has higher probability of failure. In terms of speed, we need a fast enough gate speed that we can maintain. For example, I mentioned this 10 microsecond logical cycle time. So we need to be able to maintain that type of cycle time, or even improve upon it if we can, so that we can have a computation that has the right duration, right? That can have a several week duration as opposed to, a year or more. So every factor counts here, right? We need to be able to measure and run at the physical rate of 100 nanoseconds or faster. And then we need the right reliability, right? So that each of those qubits and those operations, we have to have low error rates. And there we need low error rates that that enable us to have a physical error rate, as I mentioned in that previous plot, right, of 10 to the minus 6 10 to the minus 5 to 10 to the minus 6, right? To keep the costs down, for every hit in error rate, we require more physical resources, more qubits, to protect the underlying operations in qubits. So these are the desirables of a quantum machine: the right size, the right speed, and the right reliability. Now, at Microsoft, we're investing in a type of machine based on topological qubits. And these qubits bring those elements forward, right? So with a topological qubit, it promises a very low physical error rate, right, of roughly 10 to the minus 6, which is the desired error rate we're looking for. It promises the right size, right? It's not so small that we can't fit the electronics. And it's not so big that we expand off a module. So the nice thing about a topological qubit is, in terms of size, we can fit, fit a million on a single module and not require long distance communication. And then it has the right speed, right? So here we can target 100 nanosecond measurement time, and so we will sustain, a reasonable runtime for the overall algorithm. So topological qubits really sit in the sweet spot across these three parameters of size, speed, and reliability. And that's why we continue to invest in topological qubits, because we believe they have the right characteristics to scale, and namely to scale to that million physical qubits and beyond mark, to enable the types of applications we want to solve in chemistry and materials science. When we think about that size component, right? A key part there is, being able to wire up the chip, right? We have to be able to control and read out these qubits. We have to get signals to them, signals out of them. And so when we look at the control design, this is a picture of what control design looks like. Kind of the standard control design for qubit systems. For quantum devices. Here you have several hundred wires in this picture, and this alone, this setup is what is used to control roughly 100 qubits. So you can see it looks like a bird's nest, right? It's very complicated. So imagine now trying to scale up to 1,000,000 qubits. So it's not just the qubit scale up that matters, right? You also have to scale up the control. You have to scale up the software stack, right? The classical compute around the system. All of this has to be scaled up. And so here, when you look at this, right, it's hard to think, how are you going to get this bird's nest to scale? And so we started looking at this problem several years back, and um, came up with the following solution of cryogenic control, right? So really taking all of, a room full of racks and electronics that goes through these several hundred wires you saw in the previous slide, and really putting that down onto a single chip that sits in the cold right next to the quantum plane, right next to those qubits, to enable more scalable control. And so in our case, it's called Gooseberry. And what we've done is we've invented custom silicon that runs at 100 millikelvin. It has low power dissipation, so it won't exceed the cooling capacity of your dilution refrigerator. So I should have mentioned the qubits here. Often qubits need to be very cold, right? Almost 0 degrees. So they sit at, just above 0 there in terms of Kelvin. So, roughly 100 millikelvin is the temperature those qubits need to be at. And so we need to make sure when we wire up these fridges and wire up the qubits that we're not exceeding the cooling capability of that dilution refrigerator. So Gooseberry, this custom silicon chip that can run at 100 millikelvin, supports thousands of qubits. And what it does is it's converting those classical compute instructions to voltage signals for the qubits, and enables parallel control. We've also developed a cryogenic compute stack that can sit at 2 Kelvin. And the reason for bringing some of that up in temperature is that you can dissipate that much more heat, right? 400 times more heat. And this helps with, for example, branching decision logic that needs to be done, handling of data in the quantum machine, real-time compilation as an example. And so again, we need to sit in the sweet spot of small qubit design, small device design. It needs to be accurate, it needs to be fast. And so these cryogenic compute and custom silicon running at these different temperatures enables us to move to being able to control tens of thousands of qubits with just 3 wires, the blue wires shown here, and moving all of that electronics into the fridge itself, and right next to that quantum plane. So we can have, very robust gate operations, reasonable solution cycle times, and then also not too much heat dissipation to disturb our qubits. I want to go back to speaking about the applications and the algorithms. So when we talk about, definitely we need a quantum machine to be able to run these, right? When we look at implementation, we need to be able to implement and understand the costs of these algorithms on a quantum machine, such as the topological, based machine I just walked through. And that has to have the right scaling capabilities to scale to 1 million qubits and beyond. At the same time, our algorithms, there are nuances to the algorithm design, quantum algorithm design, we need to look at and prepare for as well when we look to scaling. And so one of the first pieces here is that quantum algorithms, they're hybrid, right? They're hybrid in terms of the types of compute, right? You have a quantum subroutine, for example, or a call to the quantum computer within a larger classical algorithm, right? So there's a very tight feedback loop between the quantum and the classical components of your algorithm. So it really is a hybrid quantum classical solution. And this is definitely true in the case of chemistry and materials. So here's a picture just bringing that to life, right? So classically, you would, for example, in catalysis, right? So classically, we would explore some different structures for the catalyst, make some new insights. And then what we do is we send to the quantum computer, and ask the quantum computer to perform one of these energy calculations for one of the steps in these reaction pathways. And so, we'll have the quantum computer enable a more accurate energy calculation, and then the classical computer is putting forward candidate structures or modifications in those in the molecular structure, in that reaction pathway, and then we send it and ask the quantum computer for an accurate energy calculation. And so we're really having the quantum computer do those accurate properties, and then the classical computer is updating, say, the model or the view of the structure we want to understand. And so this is very much a tight feedback loop between classical and quantum. So we need to develop for this, and we need software solutions and tools, platforms that enable this advanced type of compute. But it's also worth noting that this left side, right, this classical side, is very advanced in terms of the classical compute required. So this is also HPC, right? It's high performance compute, very intense classical calculations being performed, and then requesting a processing from the quantum computer. So it is very much a co-processor model when we think about quantum computing. So just to bring to life, the costs here of these types of algorithms, I want to point out that had we had this discussion, almost a decade ago, or back in 2014, right? We didn't know at that time that this could be practical, right? That we could have a practical quantum advantage for chemistry and materials science. So since 2014, there's been ample progress, right? Optimization of the quantum algorithms and understanding of the quantum algorithms for Hamiltonian simulation, which is specifically the algorithms that we're using here for chemistry and materials science. So in the case, and these apply to computational catalysis. So we've been able to bring that down 10 orders of magnitude in terms of that expected runtime of the quantum algorithm in these spaces for computational catalysis. And this has been through a mixture of both improved, mathematical understanding, better bounds on the algorithm, but also through implementation. So we've developed a whole platform, which I'll mention, called Azure Quantum, along with the Quantum Development Kit, enabling us to implement these algorithms, to debug them, to understand what is the cost, profile the subroutines, how many operations are going to be required to perform, for example, this oracle or this step. And through understanding that, we can then optimize those components and bring down the cost of the algorithm as well. And so it's really with these advances, both in tools and platforms for understanding quantum algorithms and better proof techniques as well, that we've understood how to bring the costs down on the algorithm side at the same time as working to improve the hardware as well, to bring it together to an implemented solution. So with Azure Quantum, so the types of the platform we've developed to enable this is Azure Quantum, which is available in the cloud. And here we really want to enable exploration and innovation around quantum algorithms and applications, right? So you want to be able to say build a solution, write down a quantum algorithm, taking it from its mathematical specification, right, to code, right? Program it in your favorite quantum programming language, Q Sharp, Circ, Qiskit. We've now integrated with all of those. And we also have a Jupyter notebook, hosted Jupyter notebook of environment available now as well. Also ample libraries from which to pull subroutines and operations. And we also have something now called quantum intermediate representation. And this is a representation that enables building out compilation and optimization capabilities on top of LLVM, which is a very popular open source framework for compiling. And so here, with these capabilities, you can write your quantum algorithm in code, right? Bring it forward in a programmatic fashion. Then you can integrate it with your classical compute. So as I mentioned, there are many libraries that people use in chemistry and materials science, right? Choose your favorite. We need to bring those forward and enable them to be used with quantum algorithms, right? The quantum algorithm is hybrid. We need to bring these tools together. And so with a mixture of Azure, the Azure cloud platform, as well as various industry and research libraries we've worked on to bring those together with the quantum computing environments. And then along with QIR, it enables us to bring many front ends and many different capabilities together with the quantum computing capabilities. And all of this is available in Azure Quantum. And then ultimately, what do you want to do? You want to take your algorithm, you want to test it, right? You want to debug it, you want to understand the costs, you want to simulate different instances. Of course, we can't simulate it at full scale, but for different classes of operations, you can simulate subroutines for it. And all of that is available in Azure Quantum as well. And then you can implement it on real hardware. So we do have 3 different types of quantum hardware available in Azure Quantum. We have 2 ion trap based quantum hardware systems, and then 1 superconducting qubit system. So ion traps coming from IonQ and Honeywell, and then the superconducting system coming from QCI. So you can run small instances on real hardware today through Azure Quantum. So this really enables you to explore and innovate across quantum algorithms and applications, and hopefully find that next practical quantum advantage application. But what's great is that same quantum codes, you write your code once, and then you write your code once and you can simulate, you can resource estimate, you can run a small instance, right? All with that same code and just clicks of a button. I want to give some flavor of how this is being used today, right? How is Azure Quantum being used to understand quantum algorithms and where we're going to find practical quantum advantage? So here's an example where Azure Quantum was used to reveal, for example, the core excited states of water. This is a challenging task in computational chemistry, right? Classically, very few methods probe what's called the shake-up state. This is a typical state shown in X-ray absorption spectrum. And and can be done for only very small chemical systems, right? So here we can use, for example, quantum phase estimation to calculate high energy excited states that are characterized by promotions of electrons occupying inner energy shells. And so here we can describe excited states of complex molecules, and this can have applications across chemistry and physics, materials science, biology, right? And understanding, it's really important to be able to understand these processes that are associated with the control of energy capture and transfer through photochemical processes. And of course, this has a broad class of applications across light harvesting systems, photocatalytic hydrogen production from water, facilitating proton-coupled transfer and redox reactions that enable water oxidation and other applications. So here, what you can do is you start with a molecular structure, right? You can build your molecule in Azure Quantum through a Jupyter Notebook interface. Then you can integrate it with various quantum chemistry engines like NWChem, which is from Pacific Northwest National Laboratories, a very popular computational package, classical computational package for chemistry. So you can do your classical calculations using the Azure HPC capabilities and backends. That helps you prepare the Hamiltonian parameters and trial states. And then, for that quantum simulation step you want to do, that's when you're going to then ask the quantum computer to then run a portion of this and understand the excited states from doing a Hamiltonian simulation on the quantum machine. So here we run quantum phase estimation to probe the exact energy of any given state that has a controllable error, and then we output. Once we measure that final state, the output are those excited state energies. And then what you can do is then test this out. And so this was done with Pacific Northwest National Labs, this example, and shows that with quantum phase estimation, we can get very high accuracy results here, and it has the capability to outperform classical. And you could run a very, very small instance of this on real hardware as well. So this was just run in simulation to see if this would work as a practical quantum advantage in the future. Also, you can use Azure Quantum. Here's another example where results were run on the Honeywell quantum machine. This was done with Qnesis and Eneos. And what they did is they took Azure Quantum and used it to perform an end-to-end molecular vibration analysis. So here they want to simulate the molecular vibration modes of water and methanol. And they wanted to show that quantum simulation, so running this Hamiltonian simulation on a quantum machine, could match known values, right? So they're using the Honeywell quantum machine as the backend and piping all of this through Azure Quantum. And so what they can identify is that they're using the variational quantum approach. They identify that they can get pretty close right after several thousand shots on the quantum machine. They can get pretty close to the classical results. So this is pretty exciting and a good first instance of running this analysis through on a real quantum machine and through Azure Quantum. The other pieces we have in Azure Quantum, right, we've also learned, so while we need we need super quadratic speedups for practical quantum advantage, we've also learned that we can take and emulate aspects of quantum mechanics classically and retain or gain some advantage, maybe not the full advantage we would get from running it in a full quantum system, but we can retain some of that advantage for certain classes of problems and emulate all of that classically, right? And run it on classical hardware. So in the space of optimization, we've found that we can have what we call quantum inspired optimization solutions that really are inspired by say quantum tunneling, that emulate that quantum tunneling. but still enable us to perform better than doing, say, the classical thermal jump approach in optimization algorithms. So we can, for example, get a solution faster. We could find a better solution for a fixed solution time. So these algorithms really are designed, they're classical algorithms that are designed to emulate a quantum phenomenon. And we've learned about where these work by studying quantum machines, by studying quantum devices, and studying quantum algorithms. And then we can borrow these capabilities and run them today on classical hardware. And so to bring, just give a few examples here, in Azure Quantum, we have this capability to emulate and, for some classes of problems, outperform with these classical optimization techniques borrowed from quantum, right? And so here again in Azure Quantum, you can build that solution, you can integrate with your data across Azure or across machine learning, right? Borrow other, grab your data sources from other places in Azure. And then you can take these solvers, these optimizers. You can compare across multiple optimizers. We have a handful of different solvers available in Azure Quantum. Again, these are classical algorithms running on classical hardware that give speedups and improvements today. And we also have solutions coming from our partners, OneQubit and Toshiba as well, where they have other optimization solvers that you can try and take advantage of. And so all of this scales out in Azure as well. But I want to bring this to life with a few examples. So one example is OTI Lumionics has been using Azure Quantum, but namely the optimization, these solvers that are classical, to improve their materials design approach. Right. So what they would like is to be able to have fast material design. They focus on organic LED materials. So these are, light emitting materials that are used, for example, for heads-up displays. And here they use an approach that combines, when they're looking at materials designs for these types of materials, they're combining machine learning with some simulation and property testing, and then also some actual material synthesis and validation. So with Azure Quantum, what they've been able to do is obtain quite a computational savings. So when they look at ALK3, which is a green light emitting material, for example, if you were to run this in full quantum version, it requires 42 logical qubits using a gate-based quantum device. But they can take our optimization solvers here, reparameterize the problem, and take it and get it down to a problem that can be expressed in a binary form and handled natively in one of our solvers. They can map it down to just 132 variables, perform this simulation, and dramatically then speed up and go from what would have required 42 error-corrected qubits down to something that is just 132 variable problem that can be solved with one of our classical optimizers. So this has really given them a dramatic increase in accuracy and throughput of their computational chemistry simulations that really underpin their materials design workflow. We've also used the optimization solvers and a custom solution in partnership with Case Western Reserve University to improve MRI pulse sequences. So here we are able to improve MRI scans and make them 50% better in terms of their image precision, or make them 4 times faster, those MRI scans, than the previous. And so really unlocks the possibility of better throughput through an MRI machine. If you've ever had an MRI, you probably know how long it takes, right? So making it 4 times faster can make a difference in not having to, for example, sedate a child for an MRI. 50% better image precision means dramatically improved brain imaging that can help identify, for example, if a chemotherapy approach is working well in advance or not. So these are huge unlocks in terms of medical diagnosis. And then finally, one other example on the optimization side I want to mention in terms of traffic congestion. I don't think I have, I apologize, the video, the scan isn't, this is a PDF version of the talk, so I didn't have the video here. But there's a there's a simulation that lights up how the traffic looks here. But in terms of minimizing traffic congestion, what we can use is we can use these optimization solutions, these solvers, to help improve, for example, the time you might sit, reduce the time you might sit at traffic lights, right? Or reduce the overall congestion on roads, to, really adjust ramp meters and lane restrictions, by looking at a co-routing of traffic across a large area. And using our solvers in Azure Quantum, we are able, for example, on a case that is, say, take 5,000 5,000 vehicles starting from different points in a city, here shown for the greater Seattle area, we're able to then reduce congestion by 73% and reduce commute time, for every traveler by roughly 8%. So that's a fairly dramatic improvement in congestion, and in optimizing that, by using these solvers in Azure Quantum for optimization. And that was done in partnership with Ford. So overall, Azure Quantum brings forward capabilities to study different applications and quantum advantages, right? We talked about a few today, in particular, right? Chemistry and materials science being one of the core problem spaces, the core areas we will seek quantum advantage when we have scaled up quantum machines. And again, we need a quantum machine that has 1 million qubits and beyond to really go after all of the application areas of interest. Azure Quantum brings all of this together and enables you to do quantum algorithm, research and exploration, also optimization. Here we have a variety of software tools, languages you can use. It's fully integrated with Python, with the most popular languages today, as well as Q#. We bring together solutions from our partners, and hardware from our partners, along with the ability to simulate your algorithms at different scales, and then also resource estimate how many operations are going to be required, how many qubits, right? All of this comes together with the same code, right? So you write your program once and you can use all of and deploy across all of these different backends. So it really is an end-to-end quantum stack, and it's an open cloud ecosystem. So you can contribute and also learn from the community. I want to share that we do have an offering of credits, right? Up to $10,000 of free credits in Azure Quantum. If you want to try, bring your research to Azure Quantum, try on these different hardware, try on IonQ, Honeywell, QCI, right? Try the different simulators and work to really optimize and bring forward new quantum advantage capabilities. So this QR code can take you to the credit application process. And again, we're bringing forward up to $10,000 of free credits for your research. And then finally, I just want to mention we have many customers. I highlighted a few, many customers and partners and affiliates. I highlighted a few today, but here's a snapshot of many of the different folks we're working with around the world to bring forward practical quantum advantage, and also bring forward new solutions, classical solutions that advance state of the art by learning from our quantum devices and quantum algorithms. So a big thank you to all of our affiliates and partners. And finally, I'll just close with a thank you to all of you. I hope that you learned a bit more around, what types of problems we should be looking at when we look for practical quantum advantage, what it's going to take to get there, and how you can get started today to try some new ideas and help advance us towards that, towards practical quantum advantage. So thank you so much.
Thank you very much for your presentation. So let's see if we have any questions on the chat already. All right, so we have one question by Colin. Have you at Microsoft experimentally produced a topological qubit? And if yes, then in what kind of systems? or is it just speculation, theoretical?
Right. So we have so we're working on different quantum devices there to demonstrate a topological qubit and the ability to compute and store information with a topological qubit. We continue to advance our materials stack there, our device design, and so we are internally working on demonstrating that topological qubit. And in terms of the theory and the experiment, what has been, if in case you followed the last few years, right? What has been demonstrated is we've been able to see these zero bias peaks in different devices, which is indicative of a Majorana zero mode. And then the next step is to really make that into a qubit. So there's been different devices demonstrated, not just at Microsoft, but globally, showing the right types of, let's call it statistics, to show that we do have these non-abelian anyons present in the device, and now we need to really, take that and convert it into the qubit capabilities, right? Namely, the ability to compute and store information, which requires demonstrating things like braiding and other things, braiding, measurement-only operations, and so forth. So that's what we're working on.
All right. Sounds exciting, yes. All right, we have another question by Laurent Sanchez Palencia. Do you have an estimate for the number of physical qubits needed to break RSA?
Yeah, so as I mentioned, in the case of cryptanalysis, we're looking at, it's I'll say it's roughly about a couple million physical qubits. More if your error rate is not as good as 10 to the minus 6. So, but several million physical qubits. You can move that around with a constant, depending on your physical implementation.
All right, all right. Nishant is asking, when can we expect Microsoft's own quantum machines to come online and be available for public access?
Yeah, great. So as I mentioned, we're developing our quantum machine. I mentioned that we're developing many pieces of it in parallel, right? So I mentioned about the control and the readout, and then we're also working towards really harnessing that topological qubit capability. And so, in the next several years, you'll see a this type of machine come online.
All right, and Batis Lamek is asking, what do you think about the use of quantum simulators for industrial applications?
Yes, definitely. In terms of quantum simulators, right, there's a couple different ways to think about it. I think so. I'm not sure the exact intent of this question. So there's simulation. If we want to perform quantum simulation with a gate-based quantum device, for example, what I talked about for Hamiltonian simulation, absolutely that has industrial applications, right? When we're looking at computational catalysis, I mentioned quite a few different applications around everything from fertilizer production, the carbon, improving looking at carbon capture techniques, looking at cleaner energy, right? All of these industrial applications. There are all cases where there are startups looking at more of these, actually encoding that simulation of something in the hardware itself, as opposed to taking a gate-based approach, more of a analog approach. And so those also have the potential for industrial applications. But at Microsoft, we're focused more on that gate-based universal quantum computing capability, as opposed to more of what I might call a special purpose encoding in a qubit system.
Okay, thank you.
But both have applications.
Yeah. I think wait. Okay. Then another question by Bogdan Vulpescu. Did innovation in cryocontrol for those cooled qubits take inspiration from the electronics used in space?
Oh yeah. So interestingly, um, I can say for NASA, like they've never run a, a chip that cold. So this innovation goes beyond what has been used in space, right? In fact, space, in this case, what's been used in space was run at much warmer temperatures. So this is really the first time it's been, as far as I know, that it was demonstrated at these cold temperatures. But indeed, different techniques in signal processing and some other aspects that has been used in those fields, we do take inspiration from.
I guess space would be about 3 Kelvin probably, right?
Yeah, it's warmer than we ran these at 2 Kelvin, and then as I mentioned on the compute side, but then also we have another chip running at 100 millikelvin, so
Cooler.
much colder than what you need.
Wait, did I miss? Okay, there's one more here by Colin again. In devs, the HBO drama, they showed a futuristic quantum computer that could go back in time and retrieve the voice of Jesus. Is that at all possible?
Oh man. Well, I'm gonna say no on that one, but I've been surprised.
Everything is not possible. Yeah.
Yeah.
All right. Maybe also another question. So you mentioned that I think some of your estimation used about a 100 error-corrected qubits as a reference somehow, right? So I was just wondering how, I guess it's based on some error correction codes to estimate the number of physical qubits. So how optimal do you think that those existing codes are? Is there like any margin there for
Yes.
maybe improvements?
Yeah, there's actually quite a big margin there in terms of possible improvements. The challenge is taking right. We know that better codes exist than what we've used here for these calculations. The challenge is which one of those can be implemented well in hardware. Right. So there's a balance between having, very beautiful code constructions that show you can bring these rates, way, way down and just have constant overhead. But the challenge is that many of these require, for example, long distance stabilizer measurements, meaning I have to be able to measure qubits that are very far apart on the chip. And so how do you go about doing that? In many of these architectures, you have a nearest neighbor limitation, or you have a cluster of qubits in a single node, let's say, that you can measure between. But in many of these constructions, you're going to need to be able to go beyond that, right? So how do you go beyond, your node of qubits to get simultaneous measurement information, syndrome information? So that would require going into another, often we think about, okay, can you run those connections into a third dimension on the chip, for example, another dimension on your quantum chip, and would that enable it? But it continues to look like there are some nice new code designs that don't go all the way over to LDPC codes, but have there's some new codes called Flow-K codes that are quite beautiful and look quite promising in terms of improving the overhead for error correction beyond the surface code. So there are some new techniques coming out right now, quite a few in the last few months, which is very exciting to see that progress. But there is still more to go, more to go. And if we can improve how we do our devices, think about new ways to construct connectivity and ability to jointly measure qubits simultaneously, things like that, that could help us further improve these overheads.
Okay, thank you. Okay, maybe a last question by Daniel Brown. Simulating a catalyst is one problem, but sifting through many possible ones is a different one. Any ideas on that?
Yes, yes. That is definitely a good challenge, right? You have to be able to identify a possible structure that you want to then understand those energy properties of. And so there are advanced, continue to be advances on the classical methods for doing that. Many new ideas in terms of how you could find and better identify those coming from the classical community. And I think here, the quantum computer can provide you some, I like to think of it also as like validation that your classical approach to sifting is working. So, one role for the quantum computer is to validate, yes, you found a good candidate. And then that information can be fed back to update, your model and understanding of how to find candidates. So we need continued improvement on how to find potential candidates. But I think it's interesting to think about the quantum computer providing a validation step for, yes, we were able to find a good candidate, right? By verifying, for example, an energy you might compute classically with an energy you compute quantumly. So sifting through many is a good challenge, and we should be doing a lot of that sifting, right? Grover's algorithm won't help us. It's here, right? It's too expensive with only a quadratic speedup. So we do want to continue to look at classical capabilities for sifting through potentials to send to the quantum computer. And I think there's a lot of, there's a lot of advances going on there, which are really exciting.
All right. Well, thank you very much.
Thank you.
Svore, thank you for your presentation. And yeah, with this, we finished this talk. And so just saying one announcement, we still have one presentation tomorrow at the same time for those who are interested. And it will be given by John Martinez. And so feel free to join using the same link if you're interested. And with this, we just thank you again for your contribution, and look forward to to tomorrow. Thanks a lot.
Thanks, everyone. Good night.